If you know how to calculate the Merkle root, then it's pretty easy to come up with an algorithm that will generate Merkle proof. So in this video, I'll show you how to come up with the algorithm to calculate the Merkle root, generate Merkle proof, and then verify the Merkle proof. Let's start by coming up with an algorithm to calculate the Merkle root. Let's say that we have some values that we want to create a Merkle root for. For this example, we'll say the values are A, B, C, D, E, F, and G. The first step to calculate the Merkle root is to hash all of these values. I'll denote h as the hash function. So here we're putting in the value a into the hash function h. We'll do the same for the rest of the elements. Okay, so this is the first step. Hash all of the values. The next step is to take each of these hash, pair it together with the next element, and then create another hash. So for example, we take the first two hashes, a and b, we hash them together. Take the hash of a and take the hash of b, and then pass it into the hash function again. Now to show you that this is the second level of hash, I'm gonna color this in blue. We'll do the same for the next pair of hashes, hash of C and hash of D. Put it into a hash function. E and F as well. And now notice that we have one element that we cannot pair with. We pair the hash of A with hash of B, we pair the hash of C with hash of D, and we pair the hash of E with hash of F. However, for the last element, we don't have another hash that we can pair with. So in this case, what we do is use the same hash again, hash of G. So we duplicate the hash of G. So for the last element, we take the hash of G and then pair it with itself. In general, when there are an even number of hashes, we can pair all of them. However, when there are odd number of hashes, there's going to be one that we cannot pair up with. In this case, we simply duplicate the last hash value. Okay, so this is one iteration for calculating the Merkle root. We need to keep pairing the hashes and then calculating the hash of the pairs until there's only a single hash value left. In this example, the next step is to pair this hash with this hash and then hash it again. Take the hash of A and hash of B, take the hash of C and hash of C, pair them together, and then feed it into the hash function. This is the third time that we're hashing a value, and I'm going to color this in green. And then we do the same for the right part of the hashes. Pair them together, and then put it into the hash function. Okay, so now we have two hash values, one over here and one over here. We need to do one more iteration so that we're left with one hash value. So we take this hash, pair it with this one, and this will be the input to the hash function again. Since now we only have a single hash value, this is our Merkle root. Just to summarize, the way we calculated the Merkle root was we took each individual values that we want to create a Merkle root of. We fed all of these values into a hash function. This creates the bottom level of the Merkle tree. We take these hashes and then pair them together, and then feed it into the hash function. We do the same for all of the hash values that we have at the bottom level. When there are no hash value to pair up with, we simply duplicate the hash value. We keep on pairing the hash values and then feeding it into the hash function until we're left with a single hash value. This is the Merkle root. So now we've seen an example of how to calculate the Merkle root. Now let's turn this into an algorithm. The first step was to hash individual values, A, B, C, D, E, F, and G. So the first thing that I'll do is put index on these values. Let's say that hash of A is 0, index 0, hash of B is index 1, hash of C is index 2, and so on. So we have 7 elements. Let's put this into a variable called n. So n starts at 7. So now let's try to come up with an algorithm that will take each pair of these hashes and then hash them together to calculate the next level of hashes. So this will be inside a for loop, some kind of for loop, for I equals to 0, while I is less than n, we'll increment this index I by 2. We take the first two elements, so that's a single iteration of the for loop, and then the next iteration will be at index 2. So instead of incrementing this index by 1, we want to skip the next element and go to 2. We pair these hashes. In the next iteration, we'll start at index 4. So increment I by 2. Let's say that our original hashes, array HS, array of hashes. So this will be H of A, H of B, and all the way up to H of G. For the first iteration of the for loop, we need to take the 0th hash with the first hash and then pair them together and then calculate the new hash. Let's write this in code. This will be HS and the right hash will be HS of I plus 1. And then we need to feed this into the hash function H. This code right here will calculate the next level of hashes, except for the last element. For the last element, when I is equal to n minus 1, n is equal to 7, so when I is equal to 6, it's going to look for the next element, I plus 1. So it's going to try to get this element that doesn't exist. So we need to put a bound here for I plus 1. Remember, in the case that for the last element, there's no element to the right to pair up with, then we simply duplicate this element. So we can say this, taking the minimum of I plus 1 and the last element, which will be n minus 1. This code right here takes care of the case when there is no element to the right of the last element to pair up with. Okay, so now this code will calculate the next level of hashes. But now the question is, where should we store this new hash? There are several ways we can store this new hash value. For example, you can create an array for each level and then store the new hash value into the array. In this video, what I'm going to do is reuse this array of hashes. We're going to store the newly calculated hash into the original array. So now to calculate where in this array of hashes we're going to store this new hash, let's put some indexes on these hash values for each level. For example, after pairing the hash and then calculating the new hash, we want to store this in an array at index 0. This new hash to the right, we want to store it at index 1. Okay, and the next one will be at index 2, and finally, the next one will be at index 3. Let's do the same for the top two levels as well. This will be index 0, index 1, and finally, for the last element, the Merkle root, we only need to store this in the 0th element in the array. So now looking at this diagram, it's pretty easy to figure out where we need to store the new hashes. Taking this example, we take 0 and 1, and we need to store this in the array at index 0. Going back to our code, this will be hs at index something. Let's try to figure out what the index to store the new hash is. Notice for our for loop, I goes from 0, the next will be 2, the next will be 4, and the final will be 6. How do we get so that inside our for loop, when I is equal to 0, we store the new hash at index 0. When I is equal to 2, we store the new hash at index 1. When I is equal to 4, we store the new hash at index 2, and so on. Well, if you take a moment to look at what's going on, you'll notice that all we have to do is divide the current index by 2. For example, 0 divided by 2 is 0, 2 divided by 2 is 1, 4 divided by 2 is 2, and 6 divided by 2 is equal to 3. So the index here will be I divided by 2. Okay, so now this algorithm will calculate the hash for the next level. We're only doing this for a single level. We need to keep on doing this until we're left with a single Merkle root. So now we need to run some kind of loop over this for loop. How many times should we run this for loop to calculate the Merkle root? To answer this, let's start with a simple case. What happens when n is equal to 1? So this n that I wrote over here is the length of the array of hashes that we start out with. Here we're starting with 7 elements, therefore n was equal to 7. To be explicit here, I'm going to say that n is equal to the length of the original array of hashes. So what happens when n is equal to 1? When n is equal to 1, it means that there's only a single hash value inside the array. So imagine a case where inside the array we only have a single element. Since there's no element to pair up with, this will be our Merkle root. So in this case, we only need to return the 0th element, hs of 0. So now we can put our first condition into this for loop. We can say while n is greater than 1. Since when n is equal to 1, the hash of the value is the Merkle root. Therefore, we don't need to run this for loop. If n is not equal to 1, then inside this while loop, we'll run the for loop, and let's try to update this n so that it decreases correctly. Well, let's go back to our example. In our example, we started out with n equals to 7. Here we have 7 elements. How about in the next iteration? How many elements do we have? Well, we have 4 elements. So let's say in this iteration, we somehow need to update n so that n will go from 7 to 4. And then in the next iteration, there are 2 elements. So n needs to update from 4 to 2. And finally, we have a single element. Inside our while loop, we need to write code so that n will update from 7 to 4 to 2 to 1. This part of the code looks like we need to divide n by 2. So here we can say that when n is an even number, we'll simply divide by 2 to update n for the next iteration. So when n is even, we'll simply update n by dividing by 2. How about in the case when n is odd? If we simply divide this 7 by 2, we get 3.5. Since here we're dealing with integer divisions, it will round down to 3. But what we want for the next iteration is 4. So how about we divide up? When n is odd, what we're going to do is divide up n plus 1 divided by 2. Okay, so does this code work? When n is odd, for example, when n is equal to 7, we add 1, that will be 8. And then we divide by 2, so that will be 4. Okay, so we're getting the correct result here. So this is the algorithm that we'll be using to update our n inside the while loop. But we can make one more optimization. What happens when n is even and then we also do n plus 1 divided by 2? For example, take n equals to 4, we add 1, that'll be 5. 5 divided by 2 is 2.5. Since here we're doing integer division, this turns out to be 2. Another example we can do for n equals to 2. When n is equal to 2, 2 plus 1 is 3. 3 divided by 2 in integer division will be 1. So what we found out was that in both cases, whether n is even or odd, we can use this algorithm to update n. Okay, so inside our while loop, after the for loop is done executing, we'll say n. For the next iteration will be n plus 1 divided by 2. The while loop will run while n is greater than 1. After running the for loop, which will calculate the next level of hashes, it's going to need to update this value n. In our example, we start with n equals to 7, and in the next iteration, it will update to 4, next iteration up to n, and for the final iteration, it will be 1. So this for loop is not going to run, and it's going to return the Merkle root. So this is the algorithm that will calculate the Merkle root. Now that we have an algorithm that will calculate the Merkle root, it's pretty easy to extend this algorithm so that we have an algorithm that will generate the Merkle proof. So first of all, I'm going to move this over to the side. The next part of the video is coming up with an algorithm that will calculate the Merkle proof. Let's say that we wanted the Merkle proof that the value e is included in this Merkle tree. We know the value e, so we can calculate the hash of e. In our example, to generate the Merkle proof, we have this hash, so the prover needs to provide this hash. Once this hash is provided, we can pair up with the hash that we know to calculate this hash. Once the prover provides this hash, we can calculate this hash. So now the prover needs to provide this hash. Since we've already calculated the hash up to here, pairing these two hashes together and then putting it in the hash function, we can calculate the Merkle root. We check that the proof is valid by comparing it with the known Merkle root. If they are equal, then the proof is valid. If they are not equal, then the proof is invalid. In our algorithm, what we need to do is collect these hashes that are inside the orange boxes. Let's say that to generate the Merkle proof, we are given all of the hash values. And from this, we can calculate the length of the hashes at the bottom level. In this algorithm, we need to pass this index as input. This index will be provided by the caller, and they're specifying which Merkle proof that they want to receive. In our example, index will be equal to 4, so the Merkle proof that we need to return will be the hashes inside these orange boxes. So now, how do we modify this algorithm so that we generate the Merkle proof? Since we're going to be returning an array of hashes that will be our Merkle proof, let's initialize an array and we'll call this proof. Currently, this algorithm over here will start out with the hashes at the bottom level of the Merkle tree and then calculate the Merkle root, which means that inside this for loop, we're able to know what the value of the hash for the next level of the Merkle tree is. This probably means that for each iteration of the while loop, all of these hash values are known. So if we pick the right index, we'll be able to collect the hashes that we need for the Merkle proof. So first of all, I'm going to modify this algorithm. Instead of returning the Merkle root, we want to return the Merkle proof, which will be stored in this array. Okay, let's start with the first iteration. Given that we know these hash values, given that we know this value, the Merkle proof, we need to put this hash value. So how do we do this? Let's name a variable. Let's say k. This will be the index in the array of hashes that we need to put inside our Merkle proof. For example, when index is equal to 4, the Merkle proof that we need to include is the hash at index 5. So k will be equal to 5. Okay, so now how do we calculate the correct index k? Well, we start out with index equal to 4. In this case, the hash that we need to pair with will be to the right of this hash. So this will be 4 plus 1, which is equal to 5. As another example, if you wanted to generate the Merkle proof starting here, then the first step is to collect the hash value to the left of this index. This will be hash of C, which is at index 2. Take a moment if you can figure out what the pattern here is. When the index is 4, we need to collect the hash value to the right of the index. When the index is 3, we need to collect the hash value to the left of the index. So given the index, we either need to access the hash value to the right or to the left. But how do you tell which one to get? Well, here's an easy way to tell. If the starting index is an even number, then we need to pair up with an element to the right, index plus 1. If the index is an odd number, then we need to pair up with an element to the left. So this will be index minus 1. So that's the basic idea. Let's put this into our code. If the index is even, then the hash value that we need to put inside our Merkle proof will be element to the right. This is index plus 1. And if the index is odd, then the hash value that we need to put in our Merkle proof is the hash value to the left, which will be index minus 1. So this is the basic idea for getting the correct index for the hash value that we need to put inside our Merkle proof. However, there's a slight problem with this code. In the first case, when index is even, we look at the element at index plus 1. But now, consider the case when we look at the last element, and in this case, index is even, so it's going to try to get the element to the right of it, which does not exist. So, like in this example, we need to put a bound on the index that we access. Here, we need to say the minimum of index plus 1 and n minus 1, the last element in the array of hashes. Okay, once we know the correct index to access, let's collect the hash at this index and then put it into the array of proof. Push the hash at the kth index into the array of proofs. Okay, so this code is correct for a single iteration of the while loop. What we need to do is for each while loop, we'll need to update our index. We start out with index equal to 4. In the next iteration, we need to have this index pointing at 2 so that this part of the code will execute correctly. Assuming that index is set to 2, this code over here is going to correctly find this index k to put the hash into the proof. So what is the correct algorithm that we can use to update our index from 4 to 2 and then from 2 to 1? Well, it looks like we're simply dividing the index by 2. Starting from 4, divide by 2 to get 2, divide by 2 to get 1. Okay, let me try another example. Let's say that we specify the index as an odd index 3. This is the hash value that needs to be put inside the Merkle proof. The next index will be 1. The hash value that we need to put inside our Merkle proof is at index 0. And then on the final iteration, index will be 0. And the hash value that we need to collect is at index 1. Okay, so in this case, we divide 3 by 2. And since here we're dealing with integer division, we get a 1. Divide 1 by 2 and we get a 0. Okay, so it looks like the algorithm is working correctly. What we need to do here is say for the next iteration, index is equal to current index divided by 2. And that completes the algorithm for generating the Merkle proof. We started out with the algorithm that will calculate the Merkle root, and all we had to do was extend this algorithm so that for each iteration, we pick the correct proof to put inside our proof array. Okay, and finally, let's try to come up with an algorithm for verifying a Merkle proof. Given the Merkle root and the Merkle proof, what is the algorithm that will verify that the proof is the correct proof? Okay, so I'm going to move this code over to the right so that we make some space for the algorithm of verifying Merkle proof. So let's start with the inputs. What are the inputs? First, we're going to need a Merkle root. Let's call this root. We're also going to need the proof. This will be the proof that was generated from this algorithm. Okay, we're also going to need the index that was used to generate the proof for, and we're also going to need the starting hash. Since here I'm using the letter H, I'll call this capital H. Since here I'm using lowercase h to denote the hash function. And this hash is initialized as the hash at this index. In our example, this array of hashes will contain these hashes. Hash of A all the way up to hash of G. The basic idea of the algorithm is to take this hash, pair it up with the hash inside the proof array, hash it, and then do this until all the proof has been paired and then hashed. And at the final step, we compare the Merkle root with the hash that we calculated. If the Merkle root that was provided matches up with the hash that we calculated, then the proof is valid. otherwise the proof is invalid. So now let's see what goes inside the loop. You'll need to run a for loop for each element inside this array of proof. Let's say for p in proof. Given this current hash and the hash that was provided by the proof, we need to pair them up and then calculate the hash. So let's say calling the hash function h on some hash value, we'll denote it as left and right. This left and right variable, which I have not defined yet, will either be the current hash or the proof. So let's take this example over here. We started out with index 3, so h will start out as the hash value of d. The proof will be the hash values that is inside the orange boxes. So the first element inside this proof array will contain h of c. In this example, the right hash will be this hash of d, and the left hash will be this hash of c. So that's one iteration. We put left hash and right hash into the hash function to calculate the new hash. This part of the code is pairing up the hashes and then calculating the new hash for the tree one level above. So after one iteration, this h will be this hash over here. Hash of c and hash of d. In the next iteration, the proof will be this hash of a and hash of b. The variable h will contain this value. Orange will be this left variable, and purple will be this right variable. In the next iteration, this will be the value for h, and this will be the proof. This hash in purple will be the left hash, and this hash in orange will be the right hash. Put these two hashes into the hash function, and this will give us the Merkle root. So how do we figure out what the left hash and the right hashes are? Let's look at this example to see if we can come up with an algorithm. Let's say that we start with index 3. Currently, the current hash value, which will be capital H, will be the hash value in purple box. Proof will be the hash value in the orange box. In this case, index is 3, and this will be the right hash value, and the proof will be the left hash value. In the next iteration, the hash value h will be this hash value in the purple box, and the proof element will be the hash value in this orange box. Next level above, the proof is on the left side, and the current hash will be on the right side. On the last iteration, our current hash will be on the left side, and the proof will be on the left side. This is basically what we computed when we looked at the algorithm to generate Merkle proof. Specifically, the code that we're interested in is over here. Remember, if index was an even number, then we executed this code. And when index was an odd number, we executed this code. So we can use this algorithm, modify it, and then put it inside our algorithm to verify the Merkle proof. So let's simply copy this algorithm and then paste it into here. You don't need to modify the array of proofs, so we'll remove this code. The way that the index will update for each iteration is the same, so we'll keep this. So now all we have to do is to use this part of the code to figure out which will be the left hash and the right hash. So let's go back to our example. When the index was an odd number, the proof will be on the left and the current hash will be on the right. So let's modify this code. Let's work with index equal to odd first. Then we'll say left is equal to the proof element p, and the variable right will be the current hash, capital H. Okay, and when the index is an even number, then the current hash will be on the left and the proof will be on the right. And finally, we don't need this variable k, so I'll remove this. This completes the algorithm that will verify the Merkle proof. So in summary, in this video, I explained 3 algorithms: how to calculate Merkle root, how to generate Merkle proof, and finally, how to verify Merkle proof.